So welcome. Good afternoon, everyone. Great to see a really good turnout online, and thanks for everybody. Thanks to everybody here. So yeah, before we get started, I would like to, on behalf of TISED, say that we acknowledge that McGill University is located on land which has long served as the site of meeting and exchange among indigenous peoples. We acknowledge and thank the diverse indigenous peoples whose presence marks this territory on which peoples of the world now gather. Well, it gives me great pleasure to introduce Professor Mary Kang. She's a distinguished researcher in the area of greenhouse gas emissions related to oil and gas development. Professor Kang is my colleague at TISED and in the Department of Civil Engineering. Professor Kang is really prolific researcher. She not only does research in this area of greenhouse gas emissions, but also on groundwater hydrogeology and geologic storage of carbon dioxide. I would, in terms of her background, she got an undergraduate degree at the University of Waterloo in civil engineering, right? And then went on to do master's work at University of Waterloo and then at Princeton. And then she did a postdoc at Stanford University and then joined us here at McGill. So with that, I'll turn the floor over to you and look forward to your talk.
Thank you. Thank you for the introduction. Okay. So thank you for the introduction again, and thank you for TISED for organizing today's talk. And thank you for everybody joining us here and online. Let me get started. So the title of my talk today is Methane Emissions from Abandoned Oil and Gas Wells, Measurement Data, National Estimates, and Mitigation Strategies. So here's an overview of my talk. I'm going to start with an introduction about why we care about abandoned wells and also why we care about methane. And then I'll dive into methane emissions from abandoned oil and gas wells, emissions per well, national estimates, other emitted gases, and then talk a bit about what are attributes of high methane emitting abandoned oil and gas wells. And then I'll talk about mitigation and opportunities and end with some comments about orphan oil and gas wells, which are a subset of abandoned oil and gas wells. So to begin, I want to go over the definition because the definition for abandoned oil and gas wells varies among states, provinces, territories, and countries. I'm going to be taking the definition that's in the U.S. Environmental Protection Agency in their U.S. greenhouse gas inventory. This is also, actually the definition is very similar to what's also in the Canadian National Inventory Report by the Environment and Climate Change Canada. And it's also similar to what's in the Intergovernmental Panel on Climate Change, IPCC's guidelines for national inventories. So the term abandoned wells encompasses various types of wells. Wells with no recent production and not plugged. Common terms such as those used in state databases might include inactive, temporarily abandoned, shut-in, dormant, and idle. And wells with no recent production and no responsible operator. So common terms might include orphaned, deserted, long-term idle, and abandoned. And finally, wells that have been plugged to prevent migration of gas or fluid. So abandoned wells, especially in the Canadian context, are often referred to just plugged wells, but the definition I'm using is a bit broader, so it includes unplugged wells. So there are a lot of these wells. There's approximately 4 million in the United States and 400,000 in Canada. And you can see in Canada there's a lot here in the province of Alberta, which is colored by this dark maroonish color, which represents 60% of the wells in the country. And you can see the orange dots are pretty much covering the entire province. In the United States, the top state is Texas here. You can see the orange dots covering that blue area, and followed by Pennsylvania, Kansas, West Virginia, Oklahoma, and so forth. So there are a lot of wells. So why do we care about them? I'm sorry about this figure a little bit, but important point is that, well, one of the things that we'll be discussing are methane emissions. So abandoned wells are a source of methane emissions. And when I say methane emissions, we're only looking at what is being emitted to the atmosphere. There could be subsurface leakage. So there could be methane from oil and gas formations that have migrated up, and they can go into groundwater and never reach the top to the surface and the atmosphere. But what we're going to be talking about a lot are just measurements right here at the ground surface. And just as I alluded to, there are other impacts other than methane emissions. So methane we care about from a climate perspective because it's a potent greenhouse gas. But there are other gases that come with methane, and which has air quality implications, and of course, which then has human health implications. And there's also a concern for groundwater and water quality in general. But there are some opportunities by plugging these wells. Well, it creates jobs. But there's also a potential opportunity to repurpose these wells for other uses, such as geothermal. And if you plug a well, it might allow for geologic storage of carbon dioxide, hydrogen, natural gas, et cetera. There's also some potential to repurpose the surface site for renewable or wind and solar developments. So the title of my talk had methane in it, so I'm going to take a step back and convince you that we should care about methane. Well, one reason I alluded to this earlier is methane is a strong greenhouse gas. You've probably heard that it has a high global warming potential. So 86 times that of carbon dioxide within a 20-year time frame, 25 to 32 times that of carbon dioxide over a 100-year time frame. But in any case, it's a potent gas, and we emit quite a bit of it. But there's another reason why I would say methane is interesting, and that's because there are many economically and technically feasible mitigation options to reduce methane emissions. And that's kind of what this figure shows here. And basically one of the things is, there is actually a cost to waiting, a couple decades for options to become available. So now that brings us to this question. How much methane does an abandoned oil and gas well emit? This is from a very early publication that I did. This is the first one I did came out in 2014. But I think some of the principles are the same. So key point I want to make is that methane, these are positive emissions or positive flow rates. That means methane emissions to the atmosphere. And then the negative values mean that their methane sinks from the atmosphere. That it's often due to methanotrophic bacteria eating methane. And so, and I also want to point out these are orders of magnitude. So that's 2 orders of magnitude increase, each of these increments. So what do we have here? So the red and orange lines represent wells. So just looking at forests, for example, you're looking at somewhere between 10 to the minus 1 to almost 10 to the 5. So 6 orders of magnitude variation. And I'm going to show you later, it's actually even a broader orders of magnitude variation. So methane emissions vary by many orders of magnitude. And you see that wetlands, grasslands, forests, you see that pretty consistently. I also want to draw your attention to these green bars. So these are controls or kind of several meters away from the well, kind of to represent background conditions. And as you can see, for forests, you get a lot of negative emissions because forest soils are known to be sinks of methane. And then, of course, you also get some emissions. But in general, these green bars are shorter than the red and orange bars. And you see that with forest, grassland, wetland. Wetlands are generally known to be sources of methane, so here they're all positive numbers. But still, compared to the red bars, they're not as high. So another thing I want to draw your eye to are the red versus the orange lines, which may be hard to see. So wells are required to be plugged by regulation when they're no longer producing. But as you can see, some of these orange bars are still quite high and definitely higher than the green bars. So again, methane emissions vary by many orders of magnitude. Plug wells also emit some methane. Is there a question? Okay. So, so what's important here, if you want to think about total methane emissions, are the values of the high emitters. So what are high emitters? The publication, the data that I showed you is from 2014, so it's just this little data point here, or this set of data points here. There's been a lot of other studies since then. And in general, what you're seeing is that the higher limits are somewhere between 10 to the 4 to the 10 to the 6 milligrams per hour per well range. So putting all that data together, we can ask the question, or answer the question, how much methane do abandoned oil and gas wells emit at the national scale? Well, this is from the US, but methane emissions from abandoned oil and gas wells are the 10th largest methane emitter in the United States. This is from 2017, but it's still, which was estimated in the 2019 report, but it's still generally consistent. But what I want to draw your attention to is the last column here, which is the uncertainty range relative to emission estimate. And you can see that the number 215, it's double that of the next highest one, and substantially higher than some of these other estimates. So methane emissions from abandoned oil and gas wells are the 10th largest methane emitter in the United States. It's similar for Canada, but it's the most uncertain. And we did an estimate. We also did a study taking a larger data set than what the US EPA used in their estimate, which is shown here. And so we did a bunch of scenarios using a larger data set, and basically we found that an underestimation, even with that 10th estimate, that's just this one. So, but if we looked at a broader data set, we're seeing that EPA probably underestimates by about 20%. In Canada, ECCC, or Environment and Climate Change Canada, also makes estimates for Canada, and the underestimate was quite substantial. We're looking at 150% underestimate. And, but then, I do have good news, but since that PIT publication, which came out in 2021, this year there's the new inventory report, and there was a substantial 2.5 times increase. And the main reason for that is before they were using a subset of US-based measurements to estimate methane emissions from abandoned wells in Canada. But now they were using some Canada-specific emission measurements. And so, so there was a 2.5 times increase, which matches quite a bit better with our estimates. But you know, the uncertainty range, especially in the upper range, is really large. And one of the reasons for that is that the measurement data set is small. And I think compared to other ones, it's especially small. So in the US, 1,136 wells, or actually now it's 1,146, because there was a new publication since then, measurements have been published in the United States. That's 0.03% of the 3.7 million abandoned wells in the US greenhouse gas inventory. So it's a very small percentage. And so that could be one of the reasons that we have this uncertainty. So what else do abandoned wells emit? So methane is not harmful to humans, although it is a precursor for ozone, which is harmful. But in addition to methane, abandoned wells emit other gases. So we did a measurement study in Ontario, and basically we found some of the higher emitting abandoned wells were emitting H2S, or hydrogen sulfide, which is highly toxic. And you can see that these green bars here, these are the ones that are H2S emitting. Interestingly, we don't see that compared to in the active well population. So it might be that the active well population is just better managed. There was another study done in Pennsylvania where they were looking at VOC emissions. So VOC, or volatile organic compounds, VOC emissions pose potential health impacts to nearby populations, and they're co-emitted with methane. And so they looked at a slew of VOCs, but I'm just going to point to one VOC, which is benzene. It's a known carcinogen. And benzene is detected at approximately 70% of abandoned wells in Pennsylvania. Okay, so they emit methane and other harmful gases. I kind of alluded to this before. One of the questions is, well, is there a way to predict which ones are emitting the most? So what are the attributes of high methane emitting abandoned oil and gas wells? So again, this is a follow-up study to my 2014 study. So this is all based in Pennsylvania. And so basically, we looked, so here we're removing those green bars or the controls, and we're only showing well data. Again, positive values, orders of magnitude variation. These are emissions to the atmosphere. Negative sinks from the atmosphere. Interestingly, we're seeing some negative emissions at the wells themselves, so it's just the soils right around it might be quite active. So what are we seeing? Well, let's look at the plugged wells. We're seeing orders of magnitude variation once again. But for these plugged wells, the highest one is around 10 to the 4. But if you look at this, ignore this one for now. If you look at this unplugged category, we're seeing much higher bars if you compare that bar to this bar, like a 2-order magnitude difference. So unplugged wells are emitting a lot more. Also, it's also very striking here. So if you look at these bars, you see that the tall ones are blue. Blue are gas wells. So high emitters appear to be gas wells that are unplugged. Now this middle category, there are these plugged and vented wells in Pennsylvania. Plugged wells in coal areas are required to be vented by regulation. This is for coal safety. And these ones, although they're plugged, are consistently high emitters. So high emitters are gas wells, unplugged and plugged but vented. So we went over plugging status, well type. We said these were important, so we looked at that. So I'm not going to go into this in detail, but I just want to draw your attention to the fact that these curves are different colors. So green represents Colorado, Utah, Wyoming. Blues represent Pennsylvania, West Virginia, Ohio. Red, Oklahoma. Black, British Columbia, New Brunswick. And I think the key point that I want to make is that the curves don't seem to converge or overlap. There is a fundamental difference. Maybe it has to do with sample size too, but there seems to be a difference in the distribution of emission rates based on geographical region. And so we also did a compilation, a literature review of all studies that have been done. And we do find that geographic area is consistently shown to affect or be a predictor of leakage. I just told you that gas wells are likely to be higher emitters. But that's not consistently shown in the literature, and in fact, we see conflicting results. We also see conflicting results with well age, operator, well depth, a production volume, et cetera, and time since abandonment. And so, again, geographical area appears to be a key predictor. Of course, plugging status consistently matters as well. I do want to say one thing about geographic area. These factors are not independent, and there's probably geographic area probably effectively captures all these effects, including engineering, policy, geologic effects. So the kind of takeaway is we need measurements, as of right now, we need measurements in previously unmeasured areas and data and compilation and analysis. So how do we mitigate these emissions? I already mentioned this, and that abandoned wells are required to be plugged by regulation. And what is plugging? Well, so you have this pathway. This is a very, very simplistic diagram. And you have some oil and gas. So if you take a slice through the earth in a well, you have different layers of rock containing different kinds of fluids. And so this well kind of penetrates through all those layers. So it goes to an oil and gas well, and depending on the conditions of the well and the properties of the formations as well, you can have leakage into these different formations. So the idea with plugging is you typically use a material like cement, and you isolate the zones that are required to be isolated by regulation. And so those are protected waters like groundwater and oil and gas reservoirs, and also coal areas, coal seams. At the surface, things can be different. Sometimes the wells are cut below ground and buried, so there's no surface identification. In other cases, sometimes surface markers are required. But well plugging doesn't fix all leakage issues. That's because that diagram that I showed you is overly simplistic. Okay, this is a more realistic and depiction of the well. So basically a well, or definitely a modern well, will have layers of steel casing, with basically steel pipe, and cement, and different layers of that. So it's a system, and it's there to contain fluids. But there could be failures in that system. So, and when you have those failures, then it's referred to as a well integrity issue. That's one way to call it. And those issues are not necessarily fixed when plugging. So in Canada, you are required to fix well integrity issues or surface casing vent flows and gas migration prior to plugging, but that's not the case everywhere. And speaking of surface casing vent flows, this is one of the indicators of well integrity issues in Canada in particular. In the United States, these surface casing vents are actually left open, and so they measure other things like sustained casing pressure. Just to highlight, this is a definition from Alberta regulation. SCVF, or surface casing vent flow, refers to the surface release of fluids and or gas in any combination or volume between the production casing and the surface casing. So it might be hard to see, but you can kind of make out the arrows in there. But the point is that if you have surface casing vent flow, then you have some failure in your well system. So I'm gonna mention this later, but to fix surface casing vent flows are expensive. To fix well integrity issues are expensive, but to plug wells can also be expensive. So are there any opportunities to use these wells for other purposes? So opportunities to repurpose abandoned wells. There are some. I'm going to go through this figure. I'll dive into it a little bit later. But there's geothermal, wind and solar, and geologic storage of carbon dioxide. So I said I will say a few words about orphaned oil and gas wells. First of all, what are they? Here's one definition. Orphaned oil and gas wells are a category of unplugged, non-producing wells for which the operator is unknown, unavailable, or insolvent, leaving no responsible party to plug the well and restore the well site other than government agencies and the general public. So kind of a summary here, if you have abandoned, not including orphaned, and orphaned, the key difference is orphaned wells are only the unplugged ones, where abandoned, not including orphaned, are plugged and unplugged. And the financial responsibility is the big one. So for orphan wells, there are no financial responsible operators. The government requires plugging to be done by the operator. But then if they're no longer available, the wells are left unplugged, and then the government has to step in. So the financial responsibility or state, province, or other government agency, and basically the general public. So leave it at that. So we did a data this is for the United States. So there are about 130,000 documented orphan wells in the United States. So I'm just going to draw your attention to this figure. We did this compilation twice, and we actually found a 50% increase in 6 months. And I'm going to tell you why very shortly. Well, I'll tell you now, actually. There was something called the Bipartisan Infrastructure Law that got signed in 2021, where $4.7 billion was allocated to plug orphan wells. And then so between those two times, so there was an incentive to document more orphan wells. And so what are documented orphan wells? It's a well that is documented in state databases and that has gone through some internal state verification process to determine the well as being orphaned. I will mention here that the highlight or the word documented. There can be 1 million or more undocumented wells in the United States alone. And there are undocumented wells in Canada as well. Actually, I will just say undocumented or undocumented orphan wells in Canada have not been mapped nationwide. So back to the wells or documented orphan wells in the United States. Well, how much methane do they emit? Well, they're about 5 to 6% of total methane emissions from all abandoned wells in the U.S. So this is the bar that I showed you before, which has some uncertainties. And so it's a relatively small sliver, but this uncertainty is still quite high. And for orphan wells, the assumption was we used the same database for all abandoned wells. And so, so the methane emissions from abandoned wells are generally assumed to be representative of orphan wells. We don't actually know that. So we actually probably need to evaluate differences in emission rates between orphan wells and all abandoned wells. So I mentioned this before. But maybe taking one step back, I should probably let people know that there are many orphan wells out there. So and by definition, these orphan wells are unplugged. Okay, and so the reason for that is that state programs have been, historically or consistently underfunded for a variety of reasons, and so many wells there was just no money to plug them. So in 2021, part of the bipartisan infrastructure law, $4.7 billion was allocated to plug orphan wells across the United States. So, if it was the first set of wells from September 2021 before BIL was signed, we might be okay. But if we account for inflation, we won't be. But this is the better number, 130,000. It might even be higher. Then we're definitely not okay, regardless of the inflation scenario that we looked at. So total plugging costs for orphan wells exceed U.S. federal funding. And I do want to highlight, this is just for documented orphan wells that are 130,000. There's probably 1 million or more undocumented orphan wells in the United States. And this, of course, this funding doesn't cover that yet. Okay, so opportunities. This is the same figure. So we did an analysis for orphan wells, for these documented orphan wells, and we looked at geothermal. And I'm gonna show you, dive into that a little more in the next slide. But if you and we looked at wind capacity, and so the blue bar here represents shows that about 60, almost 70% of documented orphan wells are in this top category of wind capacity potential, and they're shown in the blue areas. It might be hard to see, but the red dots are the documented orphan wells. The blue areas are this top category. For solar, we're only seeing about 20% of the top category, but you see quite a bit, almost 60% in the second highest category for solar. And so this would just be about reusing the surface surface of the site. So I mentioned about geothermal. So this figure, we only looked at enhanced geothermal favorability and not other geothermal systems like low-grade heat, something that you would find in geothermal systems in residences here, for example. That's not enhanced geothermal. So looking at that, actually most wells fall under this least favorable category, but interestingly, there's still 33% are in regions of moderate enhanced geothermal favorability. So there's a lot of potential there. And so to summarize, methane emissions from abandoned oil and gas wells, well, emissions per well vary over many orders of magnitude. Only geographical area is a consistent predictor of high methane emitting abandoned oil and gas wells. National estimates are highly uncertain. There are mitigation strategies required by regulation, and that's plugging. But we also need to fix well integrity issues, and we need to do that even for it to take advantage of the opportunities of repurposing wells for renewable energy and other uses. Finally, orphan oil and gas wells, the numbers are increasing and will continue to increase. And this is not just here, not just in the United States, it's definitely also applicable here in Canada and also globally. And this is also true as we even move to renewable energy options. These wells have already been drilled and there are still wells continually being drilled. And methane emissions and broader environmental risks are uncertain, and public funds available are insufficient. With that, I want to thank everybody for your attention, and I'm happy to take any questions. So, yes.
Is there any correlation with fracking?
So I don't know if, so is there any correlation with fracking? That's a good question. So I did an analysis for Pennsylvania, and we did some statistical analysis based on high emitting wells and locations of hydraulically fractured wells, especially high volume, high pressure hydraulic fracturing. And basically, we found no relation.
Okay.
But I mean, that's for that data set. I'm not saying that's not, it's impossible, but we're not seeing anything in the data.
Was Pennsylvania high emitting geography?
Yes, I mean, Pennsylvania is definitely, it was the second highest number of wells, but if you actually consider undocumented wells, it's the top. It's one of the top. It's, the first commercial oil well was drilled there in 1859. It's a very, it has a rich history in oil and gas development. Yep.
Is there no practical use for methane?
Yeah, of course. Methane is a valuable gas. It's actually the predominant. It's basically natural gas is all methane.
Yeah.
So yes, the challenge is here's a well, right? It's in the middle of a forest. Okay, building that infrastructure and getting that piped out. Can you use it locally? Depends on what's there. Also, the concentrations, and you also have to think about what else is in there. But I mean, there are people, and I've seen this, where people have found old wells that they connected to their house themselves and use on site. And I mean, yeah, there are opportunities to use it for on-site purposes, but there are other challenges.
Interesting talk, thank you very much indeed. Methane is very interesting because of the fact it's been increasing in the atmosphere and is one greenhouse gas, but one of the problems is it comes from different sources, and they all have extremely high spatial and temporal variability of sources. So in your cases, are there any ways of having a sort of top-down estimate of the gasity, or anything about the gas that comes out and has either isotope or
It's a good question. We're working on doing better geochemical identification. But if you look at, so we do look at ethane, and we look at the stable carbon isotope of methane. I've also looked at noble gases in the past. And there's a lot of variability among wells. So to sort that, there isn't a consistent signature. Abandoned wells have D13C values of this. That'd be great, but no, it's like a full range, because if you think about the well, there's probably some methane that's coming from that well, maybe from the oil and gas reservoir or some other shallow pockets. It could also be mixed with some microbially produced methane. So you're getting a very, it's very challenging to even figure out. You measure the methane from here. You know it's coming from this physical source. You see it. But where from the subsurface it's coming from could be so variable that it's hard to get a signature.
So you're committed to a life of uncertainty then, really, in the end. You're not going to be able to narrow it down very much. And when you have the error bars that you go from plus 215% down to minus 83%, does that mean that when people present cases for plugging the wells, that those error bars are so large that anybody could say, you don't really know?
Well, I mean, so I will say this. It is changing. I think California has changed it, but historically, or it's still today, wells are not plugged to reduce methane emissions. They were plugged originally to conserve oil and gas resources, and then later on, they were concerned about coal and mining, and then eventually they cared about groundwater, and so now some states like California are also trying to include methane and other emissions, but it's so it's never, so we don't have a good it's hard to say like plugging wells will reduce emissions by this much without direct measurements at this point.
I guess there's no online questions.
Online, yes. If national estimates give uncertain values, then which methods do you consider or recommend for methane emission measurement for larger spatial scale?
For larger spatial scale. So national estimates, I mean, there are a couple factor, like 2.5 factor estimates, and maybe uncertain. But I mean, if we can't, there are ways to reduce that by, not just brute force taking more measurements, but we are trying to do it in smarter ways by thinking about, where to go and what attributes of the wells to look at. And try to, what are the highest emitters and try to capture that whole distribution better in a more efficient way. And so for national estimates, that's one thing. But measurements at a given well it's two different things. One, to estimate, what are the methane emissions from abandoned wells across Canada? Well, then, you could use some average values. You're going to get some right, some wrong, but the errors might average out. Okay, so but if you want, it's another thing to say, here's a given a well, what are the methane, then you're looking at that full 9-10 orders of magnitude variation. So those are two very different, two big differences. So I didn't talk about measurement methods. I'm not sure exactly what the question is asking, but I didn't talk about measurement methods. But there are accurate ways to measure methane emissions from the wells. But they can be quite some could be more expensive than some people will like.
Another person has 2 questions. What is a plug but venting well?
So these are wells in Pennsylvania. So if you recall that figure where you had a well and there was a system of casings and cemented or open zones, and so basically, there's a vent at the surface, and so it's really to reduce. It has to do with reducing risk to coal mines, and so basically, it's plugged in the subsurface zones where it needs to be plugged, and then at the surface, it's vented. So there could be a lot of other gases, not necessarily coming from the plug zones, or maybe coming from the plug zones too.
The same person has a second question, which is, what is your opinion of the new published ACR methodology to provide carbon credits for plugging wells?
Yes. Okay. So there is a methodology that was published for. It's a voluntary carbon registry, so you can get carbon credits for plugging wells. There is it is specifically restricted to orphaned wells, because abandoned wells with an operator, the operator is supposed to plug them, right? So for my opinion on it, I will say something related to the previous comment about uncertainty. So for those wells, you can't just use the average emission factors that national inventory reports use, because they are designed to estimate methane emissions at national or very large scales, okay? So you get some right, you get some wrong, but it kind of averages that. That's the concept. For these wells, you have to get carbon credits, and you need to say how much is being reduced at that well. So you really need the measurements, on-site measurements. And so I'll stop there. I don't know if that answers the question. It's a very broad question. I could talk, I've given whole talks on the methodology, so I can say a lot.
And the last question, have you accounted for drill waste degrading to methane in soil or groundwater?
Can you read that again?
Yeah. Have you accounted for buried drill waste degrading to methane in soil?
Okay, yeah. No, I have not, but there could be, of course. So, we all know like landfills are emitting methane. At the end of the day, you can look at these wells, and there are wells on landfills. They're also emitting methane. We've measured those as well. So you can also think of these wells as a pathway that could actually, that allows methane to more easily flow to the surface and emit to the atmosphere. And the source could be the oil and gas reservoir, of course. It could be shallow pockets. It could be degraded waste. It could be a lot of different sources. So I did not directly account for that, but I think it alludes to the question I was asked earlier about geochemical signature. This is maybe another one of the reasons why we're seeing this huge variation. And we are trying to look at more data, more kinds of geochemical, doing more kinds of geochemical analysis to kind of narrow this down a bit. Yes. Oh, I have 2 questions. I don't know which one was first.
So do you know, it's a hotspot issue, right? Some of these wells are producing far more than others. So do you have a sort of key list of things which would tell you which would be the hot wells and hot?
That's what we're trying to figure out. And so that's the high emitter or looking at attributes of high emitters. What's actually really tricky is, the hotspots get there is kind of a geographical regional difference. There are and those differences are statistically significant. But if you go, even anecdotally, if you go to, there are certain fields, oil and gas fields. It's jargon, but basically it's a region. It's all wells in the same kind of vicinity. You can walk to them, in some cases. And so they're all wells that are relatively close, and you still see orders of magnitude variation in emission rates. Because the subsurface, it makes sense though if you think from a subsurface perspective. And the wells they might be connected. There are preferential pathways that the gas may be taking, and there are many heterogeneous. The subsurface is very heterogeneous.
Can you breed a really strong methanotroph to eat the methane that comes out and put a bit of soil on top?
Possibly. I'm not looking into that, but there's definitely maybe.
I just have a question about your sampling campaigns. So just broadly, is it, we go one time at this time of the year? Is it continuous sampling? Like how does that sampling happen? Is it seasonal? Like you go back more than once to a site?
Yes, all of the above.
Okay.
So we are very interested, and I'm trying to get more into temporal variability. But there's always a trade-off. You don't get unlimited funding, so you get a fixed amount of funding, and you have to decide, okay, do we get more locations, or do more measurements at the same well to get temporal variability? So it's a bit of a trade-off. So far, I've invested more in getting more wells. And I have some students here, and I send them out west for 12 weeks. Every year we do weeks and weeks of field campaigns, but we are starting to do more and more temporal variability. I have done seasonal measurements at a handful of wells, quite a few wells, but still, so far, the strategies have been to actually just get more wells. Yeah.
On that, are there continuous monitoring or measurement technologies out there?
Yes. So there's different temporal trends. So I have measured up to 3 years, different points in the time. So it captures seasonal variation. There's been, I've been involved in other studies that looked at 24-hour variation. And you can look at, there's different variation at different scales. And so it is something that we are looking at, but there's definitely variability at these different time scales.
Great. So I guess with that, please join me in thanking Mr. Kang for this great presentation. And thanks to all of the audience who joined us from online, from all over the world. And thank you all for being here.
Thank you.